Today's going to be a shorter video on electrolytes. So before we start talking about specific electrolytes, let's talk about where most of the electrolytes are found. So if this is a cell, this is your extracellular fluid, and this is your intracellular fluid. Then we look at the extracellular fluid first, and sodium and chloride and bicarbonate are in higher concentrations in the extracellular fluid. And then in the intracellular fluid, potassium, magnesium, and hydrogen phosphate are higher inside the cell. So what makes these electrolytes is that they all come with a charge, either a positive charge or a negative charge. The positively charged ones are called cations, and then the negatively charged ones are called anions. The total electrolyte concentration will affect water balance. So in the extracellular fluid, we're really talking about sodium because it is in such high quantities in the extracellular fluid. So the more sodium you have, then the more shift you're going to get from the intracellular to the extracellular fluid. And so that really affects water balance. But the individual electrolytes is what we're going to concentrate on more today. The concentrations of the individual electrolytes affect the cell function. So how much potassium is inside the cell, that's going to affect the electrolytes. How much chloride specifically is outside the cell, or how much sodium outside the cell, or how much bicarbonate outside the cell. These are the individual electrolytes that affect the cell functions, and so that's what we want to talk about in this video. The normal sodium concentration in the extracellular fluid is around 140 milliequivalents per liter. And then if we look inside the cell, there is sodium inside the cell, but it's such a lower concentration, it's only 10 milliequivalents per liter. So you can just see how much more concentration there is outside for sodium than there is inside the cell. Then if we look at potassium, potassium has a higher concentration inside the cell. It has 160 milliequivalents per liter inside the cell. And then outside the cell, there is some potassium, but it's only 3.8 to 5.0 milliequivalents per liter. So there's quite a big difference. So we don't really have to memorize those numbers, but we do need to know that potassium has a much higher concentration inside the cell. Sodium has a much higher concentration outside the cell. And if those levels are disturbed, it's going to affect the cell function. Most of the sodium in the extracellular fluid is it's not really floating around freely. It will be in the form of sodium chloride or sodium bicarbonate. Sodium imbalance is the most common problem with electrolyte balance. Problems with potassium are less common, but they are more dangerous. The most dangerous problems with electrolyte balance then are caused from potassium imbalance. If potassium inside the cell is too low, it can cause things like muscle weakness. It can even cause paralysis. Because remember what sodium and potassium do, they help to set up that transmembrane potential. And if potassium is too low, it's basically hyperpolarizing the cell. So it's going to take that much more of a stimulus to get that cell to threshold. So if it's too low, you get muscle weakness and paralysis. But if it's too high, and it's in a cardiac cell, that can lead to cardiac arrhythmias. And so both of these are much more dangerous. So potassium's much more dangerous, even though sodium imbalance is much more common. So let's go ahead and talk about sodium. So sodium, we already said, is mostly in the extracellular fluid. We gain sodium through the digestive tract, so we're gaining it through diet and drink. And then we're losing it through urine and perspiration. To be in balance, the gains need to equal the losses. And those are going to be anywhere from 1.1 to 3.3 grams of sodium per day. In order to keep the sodium concentration constant, there has to be a gain or loss of water to keep it constant. So we have the cell and we have sodium. So we have a certain amount of sodium in the extracellular fluid. So it's really, we're not really trying to add and subtract sodium to keep that balance there, to keep the right concentration there. Instead, the body will add water to dilute it, or it will take out water in order to make it more concentrated. So this is kind of how we keep the concentration of sodium constant. At the same time, it's maintaining that extracellular fluid volume. And remember, the extracellular fluid is the interstitial fluid and then also the plasma. So whatever is increasing or decreasing in the intracellular fluid is also increasing or decreasing in the blood vessel. So we're basically helping to maintain blood pressure this way. So these are some of the functions of sodium. So number one, sodium plays a major role in maintaining blood volume and blood pressure by attracting and holding that water. It's also important in cellular osmotic pressure. So to get fluids in and out of the cell. So this is the shift between extracellular and intracellular fluid. And it also is important in transmitting nerve impulses. It's also helpful in the GI tract. So when sodium is reabsorbed, or when sodium is absorbed from what you've eaten, so when it's absorbed from your diet, it brings water with it. So it increases water absorption from the digestive tract, and that will help to elevate blood volume and blood pressure. Let's talk about a couple of conditions that involve sodium. So first of all, let's talk about hypernatremia. So hypernatremia basically means that the sodium gains exceed the losses. So if we looked at the cell, we would just say that we have an increase in sodium concentration in the extracellular fluid. That is hypernatremia. Hypernatremia actually means of the sodium in the blood, but we've already gone over how the plasma and the interstitial fluid exchange ions and fluids quite readily. Hypernatremia is a common electrolyte problem. It's defined as a rise in serum sodium concentration to a value that exceeds 145 millimoles per liter. So you should know the normal values of sodium. The normal values are 135 to 145. Anything over 145 means there's too much sodium, and that's hypernatremia. Hypernatremia can be caused by things like dehydration, where you're losing water but you're not losing sodium, so the sodium concentration increases. It can also be due, like we said before, to vomiting and diarrhea. It can also be caused by sweating. And it can be caused by high fevers. It can also be caused when you are just eating a lot of salty foods like salty chips without drinking any fluids. It can also be caused by drugs, like steroids can cause hypernatremia. It can be caused by certain blood pressure lowering medications. And it can also be caused from licorice. People at risk for hypernatremia include the elderly who aren't eating enough. So if they're not eating and drinking, they're not getting enough sodium in. People with uncontrolled diabetes. So if they have uncontrolled diabetes, they're losing a lot of glucose in their urine, and water's going to follow that glucose, so they're going to be urinating a lot. Also, people that are on diuretics, they'll be losing a lot of fluid, which is going to it's going to concentrate their sodium in their extracellular fluid. So those are just some examples of people that are at risk for hypernatremia. So that's hypernatremia. So again, hyper means too much, Na sodium, and then emia means in the blood. So hypernatremia means high sodium levels in the blood. Now let's talk about the opposite condition, which is called hyponatremia. Hyponatremia means that you have a decrease in sodium level that's below normal. So here's your cell. You have decreased sodium in the extracellular fluid because you're also going to have a decreased sodium in the blood. So again, the normal sodium level in the extracellular fluid is 135 to 145 milliequivalents per liter, or millimoles per liter, right? And so hyponatremia will occur when the blood sodium level goes below 135. That's what hyponatremia is. If the sodium level is too low in the extracellular fluid, that means that it's pretty dilute. And so water is going to actually flow into the cells to try to balance out the sodium concentration inside the cell versus outside the cell. So then the cell is going to start to swell. This swelling can be dangerous, especially if it's in the brain, since the brain can't expand past the skull. Low sodium in your blood can be caused by having too much water or fluid in the body. This dilution or watering down effect makes the amount of sodium seem really low. So the cause would be overhydration, where you're drinking too much pure water without supplying any electrolytes along with it. Low blood sodium can also be caused to losing sodium from the body or losing both sodium and fluid from the body. So in that case, that would be sweating. If you're sweating and you're losing, excessive sweating causes a loss of sodium. That can also cause hyponatremia. It can also be the result of some different diseases and medications. Kidney failure might cause hyponatremia. The kidneys can't get rid of the extra fluid from the body, so then the extracellular fluid becomes dilute. Congestive heart failure. This is where there's an excess of fluid gets built up in the body in the form of edema. Antidepressants and pain medications. They can cause more sweating or urinating than normal, so you're getting rid of sodium that way. And excessive thirst. So these are just some ways that you have more fluid in the body, and that's diluting the sodium in the extracellular fluid. The fluid levels in your body that sodium is helping to balance have a lot to do with blood pressure. So I just want to go over this in blood pressure. I think that you already know this, but I just want to mention it anyway. So if you have an increase in extracellular volume. So here's your blood vessel, and then this is your plasma inside here, and this is your interstitial fluid, and then again you have your cells, right? So if the fluid increases, so if the plasma fluid increases, then the interstitial, of course, will increase. So if they're increasing, that means that your blood pressure is going to increase. So your blood volume goes up and your blood pressure goes up. If it goes up too high, then the natriuretic peptides will be released from the heart because the pressure is stretching those walls of the heart, and then water will be lost in the kidneys, right? It'll be excreted in urine and it'll be lost at the kidneys, so that'll help to bring that blood volume back down and bring the blood pressure back down. If, on the other hand, the extracellular fluid volume decreases, so you have less water in the plasma and less water in the interstitial fluid, then you have a decrease in blood volume and you have a decrease in blood pressure. And if it decreases too much, then that will activate the RAAS system, where renin is released, and renin causes the conversion of angiotensinogen to angiotensin 1 to angiotensin 2 at the lungs, and then that is a major vasoconstrictor, and that will increase blood pressure. Then ADH is released, and that causes you to retain fluids, so then that also increases blood pressure. And aldosterone is also going to be secreted because of renin, and that's going to increase both water and sodium retention. So now let's talk about potassium. 98% of potassium is in the intracellular fluid. We gain it through the digestive tract, so we gain through diet and drink. And then it's lost in the urine. Potassium is very important. It functions to help regulate fluid balance. It's also important for nerve signals. And it's also important for muscle contractions. So if you think back to all the physiology that we learned, you remember that we talked about potassium helping to maintain that resting membrane potential and being involved in action potential generation as well as muscle contractions. Potassium is going to be excreted in the kidney tubules. So if we look at our tubules here, and we look at the blood, if potassium increases in the blood, then more potassium will be excreted. So sodium will be reabsorbed, and at the same time, potassium will be secreted so that it will get excreted in the urine. However, if the blood is too acidic, if there's too many hydrogen ions, then instead sodium will be reabsorbed and hydrogen will be secreted in place of potassium. If aldosterone is present, aldosterone causes an increase in sodium reabsorption, so sodium becomes reabsorbed more readily, and that means that potassium then will be excreted more readily. If there is an excess of aldosterone being secreted, that will cause a situation where too much potassium is being lost in the urine. And in that case, a person would have hypokalemia. Hypo meaning too low potassium in the blood, because they're losing too much blood because aldosterone is causing an increase in sodium reabsorption and a consequent increase in potassium secretion. So the most common cause of high aldosterone levels is an excess production of aldosterone from the adrenal cortex. The most common cause of excess aldosterone production is a tumor of the adrenal cortex. And one type of tumor that you might hear about is called pheochromocytoma. So that's a pretty rare tumor, but it will cause the adrenal cortex to increase the production of aldosterone. So more sodium is reabsorbed, and at the same time potassium is secreted, and then potassium is lost in the urine, and that leads to hypokalemia. So a decrease in potassium in the blood. So if you have a decrease in potassium in the blood, that's called hypokalemia. And on the other hand, if you have an increase in potassium in the blood, that's called hyperkalemia. We're going to talk a little bit about a couple more of these electrolytes. Let's look at calcium. So before we talked about sodium, and sodium is the most common electrolyte in the extracellular fluid. And then we talked about potassium, and we said potassium was the most common electrolyte in the intracellular fluid. And now we're taking a look at calcium. Calcium is the most abundant mineral in the body. It's stored in the skeleton. And gains and losses can be through bone remodeling. So if you remember what happens with the osteoclasts, they tear down the bone and they release the calcium into the blood. So osteoclasts release calcium into the blood. And then the osteoblasts, they lay down new bone and they remove calcium from the blood so that they can pack it into that new bone that was being built. Additional gains from calcium are from diet and drink, so from the digestive tract, and also we have losses of calcium through the GI tract, so through feces, and there's also losses through the kidneys through urine. So calcium has functions in the body to make your bones and your teeth strong. It also functions in muscles and nerves. So we've already gone over all that physiology earlier in the year, how calcium is necessary for muscles and also how it's necessary for nerve conduction. If a person has high calcium levels, that's called hypercalcemia. Calc meaning calcium, emia in the blood, hyper, too much. And low calcium levels then is called hypocalcemia. Now, calcium levels are controlled by hormones. Both PTH and calcitriol control when calcium is being reabsorbed in the body. So if PTH and calcitriol are present, then there will be an increase in calcium in the blood. PTH causes the osteoclasts to release calcium into the blood. It causes the kidneys to retain calcium, and it causes the digestive tract, so the intestines, it causes them to absorb the calcium from your diet. And it does that by stimulating calcitriol. On the other hand, the hormone called calcitonin is secreted from the thyroid gland. Calcitonin lowers calcium levels in the blood, or decreases calcium levels in the blood. And so it will do that by stimulating the osteoblasts so that there's a place for calcium to leave the blood and be packed into that new bone. It stimulates the kidneys to secrete or to excrete calcium in the urine, and it also will decrease the amount of absorption in the intestines. The normal level of calcium is 8.5 to 10.2 milliequivalents per liter. So you need to know the level of these electrolytes. In order to maintain that, adults have to absorb about 0.8 to 1.2 grams per day of calcium. Next, we're going to talk about magnesium. Magnesium is found in the skeleton and the extracellular fluid. You have to take in about 0.3 to 0.4 grams per day, and a lot of people are deficient in magnesium. It's needed for more than 300 biochemical reactions in the body. And so it just has many, many different functions. It helps to maintain normal nerve and muscle function. It supports a healthy immune system. It keeps the heartbeat steady. It helps the bones to remain strong. It helps to regulate glucose levels. And it also helps in producing energy and protein. So there are a lot of functions of this important electrolyte. We also want to look at phosphate. So phosphate is needed for bone mineralization, for ATP production, of course, because ATP is adenosine triphosphate, right? For creatinine, phosphate formation. So basically, it's necessary to form high energy compounds. It also is necessary to activate enzymes and to make nucleic acids. So nucleic acids like DNA and RNA. Then we have chloride. Chloride is the most abundant anion in the extracellular fluid. It helps to balance fluids inside and outside the cell. And it's also necessary to make hydrochloric acid. You remember when we talked about the chloride shift. Okay, so that's it for our electrolyte lecture, and the next video that we will be talking about acid-base balance. We'll see you then.